Hey everyone, welcome back to our channel. Today we'll be diving into an exciting chapter from the Brain Facts book, Chapter 5, which is all about thinking, planning, and language. These are the processes that shape our daily lives, so let's explore how they work. From the moment you wake up, your brain is bombarded by stimuli. The sound of birds singing, the smell of coffee, the warmth of sunlight streaming through your window. Fortunately, your brain is adept at filtering this flood of information and making decisions about what actions to take. But how do you think? What is happening in our brains when we decide what to wear or how to solve a problem? Let's break it down. The first step is perception. This arises from the senses which process the world around us. Next, the brain interprets these perceptions by comparing them to memories of past experiences and observations. Constructing representations is a crucial part of this process. Our brains build simple representations of people, places, objects, and events to make sense of our moment-to-moment perceptions. For example, you can still identify a dog even if it's a different breed or color than what you've seen before. A bicycle still registers as a bicycle even if only one wheel is visible. Now let's talk about language. Language is a complex cognitive ability involving several areas of the brain. For instance, Broca's area is vital for speech production, while Wernicke's area is crucial for understanding speech. These areas work together to allow us to communicate effectively. Damage to these areas can result in language disorders, which shows us how specialized and interconnected our brain functions are. So, how does this all come together? Through the brain's ability to construct hierarchical, connected representations of concepts, we build meaning. This involves the parietal cortex, which helps us understand numbers and their meanings, and the occipital temporal cortex, which aids in visual recognition. These brain regions help us understand symbols, such as recognizing the number 3, and connecting it to concepts like 3 objects or the rhythm of a waltz.
What happens when there are issues with language processing? Well, scientists gained some insight into the consequences of damage in areas with language processing after examining a series of patients who exhibited strange symptoms. The most famous of these patients was Victor Leborn, who could only speak a single syllable and nothing else, tan. Towards the end of his life, he met a physician named Paul Broca, who realized that Victor was able to fully comprehend what others were saying but could only reply with tan. After Victor's death, Broca discovered damage in a portion of the frontal lobe. This region in the left hemisphere, now known as Broca's area, is responsible for speech production. Since then, we have learned that damage to particular regions in the left hemisphere result in language disorders, known as aphasias. Damage to Broca's area is known as Broca's aphasia, or non-fluent aphasia, in which speech production is impaired but comprehension is intact. Symptoms include slow speech that requires great effort, often lacking complex structure. Sometime later, a German physician named Karl Wernicke met a patient he referred to as SA, who also had unusual symptoms. She could speak fluently, but what she said made no sense. She had absurd answers, made up words, and had difficulty naming objects. After her death, Wernicke found that she had damage in a region of her left temporal lobe, an area that we now know is responsible for comprehending speech. People with Wernicke's aphasia, or fluent aphasia, can understand simple words and have a normal speech tone, but have many errors in word selection and sentences can be unintelligible. Yet another type of aphasia is called pure word deafness, which is caused by damage to the superior temporal lobes. Contrary to its name, people with pure word deafness are not actually deaf. They can hear music and speech and detect the tone and emotion of the speaker. However, they cannot link words to their meaning or understand what is being said. You can think of it like hearing someone speak a foreign language. You can hear the person speaking, but you have no idea what is being said. People with pure word deafness can, however, process written language, since that's processed in a different brain region. From these studies, scientists have realized that producing complex speech is strongly dependent on the left hemisphere. although speech requires both lobes to be fully functional. Reading and writing require additional brain regions, including those that control vision and movement. Several genes are associated with language processing. One of them is FOXP2, which codes for a special type of protein that switches other genes on and off in particular parts of the brain. Mutated FOXP2 results in difficulty making mouth and jaw movements, in addition to difficulty with spoken and written language. Much of what we know about these genes comes from birds, who also have similar genes to help them sing. We now know that baby birds learn songs by imitating a vocal model, such as a parent, just like human babies learn speech in an early developmental period. Interestingly, FOXP2 mutations can disrupt song development in young birds, just like speech disruption in humans. The dorsal striatum is one brain region that expresses high levels of FOXP2 product. Located in the basal ganglia, the striatum's ability to transmit information is disrupted in FOXP2 mutation. Other brain regions are currently being studied for similar roles. Portions of the middle and inferior temporal lobes have been found to participate in accessing the meaning of words, and the anterior temporal lobe is being studied as a site that might participate in sentence-level comprehension. The left posterior temporal lobe contains a sensory motor circuit for speech, thought to help communication between the systems for speech recognition and production.
Now let's dive into some of the most fascinating processes occurring in the prefrontal cortex, or PFC, the outer folded layers of the brain just behind your forehead. The PFC is like the brain CEO, managing and supervising everything. It takes in sensory and emotional information to plan and execute decisions and actions. This area supports key executive functions like selecting, rehearsing, and monitoring information from long-term memory. It interacts with other brain areas that handle visual images, sounds, words, and spatial locations. It is also one of the last regions to developing until 25 years ago. While humans have a highly developed PFC, other animals also display executive functions. For example, studies in non-human primates show that their PFC neurons keep information active while they complete tasks, similar to our working memory. Executive function is a blend of three core skills: inhibition, working memory, and shifting. Inhibition is the ability to suppress actions when they're inappropriate. Even toddlers show early signs of this by delaying eating a treat. By preschool, kids can tackle more complex tasks, like Lucia's hand game, which tests their ability to inhibit automatic actions. Working memory is the ability to hold information temporarily while deciding how to act. It depends on both the PFC and the parietal lobe, enabling us to remember a phone number or a list of items briefly. Shifting, or mental flexibility, lets us adjust our behavior when conditions change. In a card sorting task, for example, children learn to switch from sorting by one rule, like color, to another, like shape. As children grow, their ability to shift between tasks and monitor errors improve. By mid-adolescence, these skills reach adult-like levels, involving many regions of the PFC. While the PFC is crucial for executive functions, it uses inputs from across the brain. Interestingly, as these circuits mature, their activity decreases, becoming more efficient.
Imagine you're in a candy store with two choices, chocolate or gummy bears. Tough call, right? Well, your brain is doing some heavy lifting to make that decision. Let's break it down. This is your brain, and it's got some cool tricks up its sleeve. First, it uses something called executive functions: inhibition, working memory, and shifting. Think of these like your brain's superhero team. They help you weigh options, understand the rules, plan ahead, and predict what might happen. So you've got inhibition saying, hold up, let's not eat all the candy right now. Working memory reminding you, remember, you promised yourself only one treat. And shifting, helping you decide, okay, maybe I'll try gummy bears instead of chocolate. Now, different types of decisions use different parts of your brain. Logical decisions, like figuring out the quickest way to your friend's house, uses the lateral prefrontal cortex, or PFC. It's like the brain's GPS.
But when emotions are involved, like deciding whether to accept a cigarette from someone you're trying to impress, the orbitofrontal cortex kicks in. This part is all about rewards and punishments. The PFC helps us control our impulses and make better decisions. Fun fact, it's one of the last parts of the brain to fully mature, usually in your late 20s. That's why teenagers sometimes struggle with controlling their emotions and impulses. Sorry, teens, but there's a reason your parents think you're impulsive. Now, let's switch gears and talk about social neuroscience. Humans are super social creatures. We love hanging out with friends, understanding others, and sometimes even reading minds. Not literally, of course, but our brains are pretty good at it. When we interact with other parts of the brain, like the medial prefrontal cortex, MPFC, and the temporoparietal junction, TPJ, are hard at work. They help us read social cues, choose the right responses, and understand others' thoughts and feelings. This process is called mentalizing. It's like having a superpower that lets you understand what others are thinking and feeling. Ever wonder why you can sometimes just tell what your best friend is thinking? That's called mentalizing in action. Speaking of superpowers, have you ever heard of mirror neurons? These are special neurons that fire not only when you do something, but also when you see someone else do it. It's like having a built-in mirror reflecting others' actions. Mirror neurons help us learn by imitation and understanding others, but there's still some debate about how important they are for empathy and social understanding.